Microphone is on and in talk. Testing 1 2 1 2 1 2. Nice. Start talking.
Oh, address. Cease and desist. Sit down, be quiet, listen. Exciting.
It's exciting.
So, I had a hard time presenting it. Turn off the lights.
Where's the light switch on that?
Light button panel. I'm going to use the 3 guiding principles of zeal, ignorance, and brute force.
There we go. Excellent.
Sorry, Dave.
All right. Greetings, everyone. My name is Sam Falvo, and I have some news to give everybody. I am once again gainfully employed. The bad news is that I'm gainfully employed. So I have an agenda for this talk, which is unusual because normally I'm very ad hoc. But I want to go over kind of like an evolution of electrical interconnects, which colloquially I refer to as buses because that seems to be the thing in the industry, even when they're not technically buses. So we're going to start out with your very simple 3-state shared bus. Everyone knows this. If you've ever used a Z80 machine or a 6502 machine, those are all 3-state shared buses. And then we'll move on to why the Wishbone bus came about. I'll discuss how flexibly you can use Wishbone in what's called interconnects. This is why one of the reasons why I refer to the actual interconnects as buses, because in Wishbone terminology, interconnect has a very specific meaning. And then I'll get into more Kestrel specific things, like, for example, why I'm moving away from Wishbone B3 and adopting Wishbone B4. Excuse me. A sneak peek at an upcoming Verilog project of mine, the KCP 53010. It's the next generation RISC-V processor that I'm currently working on. I make it sound more important and bigger than it actually is. It's basically just me finally getting around to redoing the processor the way I think it should have been done the first time. And then finally, I'll get into the optional stuff, things like error handling and retry handling, and so forth. So a good example, like I said, of the 3-state bus would be my Kestrel I from like 2004, maybe, somewhere around there. These buses are extremely cheap and easy to make. You just wire a bunch of chips together. D0 goes to D0, goes to D0, etc. There is a complication in the sense that you're allowed one and only one bus master. That is to say, whoever's in charge of the bus at the time. All other devices that hang off that bus are called slaves, or master slave. So if you need to use multiple bus masters, which most computers do at some point, especially if you have a video chip, you have to add circuitry like arbiters, for example, things that when you request control of the bus, something has to say, okay, processor has the bus until time t0, and then I'll switch over to you or whatever. This used to be integrated right into the processors themselves. So if you use a Z80, there's a bus request line, for example. And if you use an 8086, there's a hold line that when you assert, after the CPU is finally done doing what it's doing, it then responds with a hold acknowledgement, HLDA. That's where that signal comes from. Come the 80286 based machines, IBM was like, you know what, we really need to up the ante here. So they came out with microchannel. And that was, I remember when microchannel came out, it was a big, big thing in the industry because for the first time, bus arbitration was not placed on the CPU, even though the 286 and the 386 still had that circuitry on them, and I think were first used. The bus arbitration mechanism was actually off the chip. So that was kind of a big thing back then. But when you want to integrate it onto, say, an FPGA, which is a common thing that you might want to do these days, then you run into problems. So FPGA vendors and actually even people engineering with these, at the time, very expensive chips, would try to replicate these old three-state shared bus systems on the FPGA itself. And there were two things working against them. One, at the time, they had fairly poor timing analysis. And number two, these chips were awfully expensive. And as anyone who is a reader of Robert Grossblatt knows, you really can't afford to use a chip unless you can afford to blow it up. And at the time, these chips were $50 a pop minimum. Most likely, probably several hundred. So as a result of this, let me advance my notes here. As a result of this, engineers tended to avoid the use of three-state buses on the FPGA chip itself. There is actually a third issue as well, which is when you route signals onto a three-state bus, you have to overcome LRC time constants. That is to say, you have to overcome both inductance and capacitance of that signal. And as a result, they tended to be fairly slow. So yeah, FPGA vendors, they saw the trends and eventually dropped support for three-state interconnects inside the chip. This is not to say that you can't use three-state buses outside the chip. They have actually, when you look at a layout of an FPGA, the internal logic blocks are very different from the external logic blocks. The external logic blocks actually do support three-state operations, but if you look at the internal circuitry, they no longer do. So as a result, all of these engineers and FPGA vendors, they would all come out with, oh, well, if you're trying to replicate this kind of behavior, here's how you would do it. And all these here's how you would do it, they tended to be very ad hoc, and there was like no real standardization at the time. So eventually, as you might expect, where there's a will, there's a way. And the will was, we really, really, really want to have standardized IP blocks that we can sell to anyone, but that requires that we have standard interconnects. And so that's how things like, for example, AXI, AHB, Wishbone, and OCP, there are many, many others that came out as well, right? So in this particular talk, as I said, I'm going to talk about Wishbone, but OCP is actually like the granddaddy of them all, in a way. OCP, if you look at the specs for that, it's like 900 pages long, and Wishbone, you can kind of say, is a design subset of OCP. But I'm sure that if you squint hard enough, you'll find that AHB is also a subset. So there's different interconnects that one can use. So there are two revisions of Wishbone. And it is an open source interconnect, which is partly why there are only two revisions. It is originally authored by a company called Silicor Incorporated, which is no longer in business. but is now overseen by an organization called Libre Cores, indirectly through open cores. And basically, there are two modes, or two modes of operation, essentially, that govern how you interpret signals on the Wishbone interface now. Because I'm not really going to talk about B3 per se, but rather B4. There's the B4 standard mode, which is essentially the legacy B3 operation. And then you have B4 pipelined. The two are not directly compatible with each other, but you can build simple circuits that actually make them so. They both have common traits, though. They're both very easy to understand. The actual standards document is like maybe on the order of 84 printed pages long, and that's including lots of timing diagrams and explanations and lots of formal verbiage and stuff like that. It's actually a pleasure to read. It is extremely high performance as buses go. There are, to this day, debates over whether or not AXI4 is as performant as Wishbone and vice versa. Some people think it is, some people think it's not. It depends on your application. But it does have 68,000 bus like asynchronous handshake protocol that allows you to interface to very slow devices. But it also allows you to complete bus transactions in single cycles as well. So it can be at least as fast as PCI, or it could be as slow as 68,000. It's all up to you. It is incredibly low overhead. Wishbone B3, for example, takes up maybe a small handful of lookup tables to implement on an FPGA. And B4, maybe a little bit more than B3, but not a whole lot. It's certainly much smaller than AXI, if you were to compare it to that. AXI has 5 separate channels. They all can operate independently. Wishbone doesn't have a channel architecture like AXI does, but on the other hand, it takes up 1/2 to 1/3 the number of cycles, or the number of signals that you have to deal with. And if you do want to use multiple channels, Wishbone's solution to that is just route multiple Wishbone interconnects. And the primary difference between B4 and B3, though, is that there's a very clear separation of concerns between the circuitry that is responsible for requesting memory and the circuitry that's handling the response from memory. So here's an example set of timing involving Wishbone B3. And what you can really see in this, the lines that are colored in red, the cycle, the strobe, and the acknowledge input. Basically, when cycle goes high, or is asserted, basically, you're requesting access to the bus. And when strobe goes high, that's when you are actually using the bus, right? 99.9% of the time, those two will go high at exactly the same time. And in Wishbone B3, they will go low at exactly the same time. So in a sense, one of these signals is superfluous. The acknowledge signal goes high when the bus transaction that is currently operating completes, as you might imagine. And so here we're showing 2 transfers that takes up a grand total of 5 clock cycles. But what you'll notice is the second bus transaction doesn't start until the end of the first bus transaction. So in a sense, we're using up over this set of 5 clock cycles. We are always driving this bus, and there's no opportunities for exploiting parallelism. There's no opportunities for there's an implicit assumption, if you will, that the interconnect fabric on the FPGA is fast enough that it will route signals from point A to point B all the way across the die in a reasonable period of time. So Wishbone B3 is great if your clock speed is low. But as you drive the clock speed high, propagation delays become increasingly relevant. Which is why Wishbone B4 pipeline basically came about. Now, if you'll notice, all the bus transactions are scrunched up into the first 2 clock cycles. this transaction. So we're still taking up 5 clock cycles. But you'll notice that the strobe output goes low at the end of the final command that's being sent. At this point, we haven't even received any acknowledgement concerning the first transaction on the bus. When the transactions do happen, though, we see the pulses on the acknowledge input line, and we notice that even though the 2 transactions happen back to back, clock to clock, there's a wait state in there, right? So we acknowledge the first one, then we wait another cycle, and then we acknowledge the final one. When that transaction completes, then and only then does the cycle output drop low. So we see a couple of things here. First of all, the circuitry or the mechanism that handles sending the requests out on the bus is independent from, hey, I need the bus, right? It's a completely separate circuit. Likewise, the circuitry that handles the receipt of the data, if any, is a separate chunk of circuitry from that which sends the stuff out. All right, so let me talk about how the Wishbone devices are actually put together on the FPGA itself. So we have, in this hypothetical circuit, 3 bus masters. So it could be a microprocessor, a video chip, and an audio chip, for example, or core, I should say. And we have 4 slave interfaces. Could be memory, could be RS-232, what have you. Now, in this case, we're emulating a shared bus, just like we would have with a Kestrel 1, for example. And we do this by taking all the buses from all of our masters, and we combine them using basically a gigantic OR gate. And we do this signal for signal, right? So we take master 1 data pin 0 and we OR it with master 2 data pin 0, with master 3 data pin 0, etc. And the way we coordinate who has control over the bus is, again, we need that separate arbiter, and that arbiter tells the masters, hey, you can drive the bus, or you can drive the bus. So internally, it's all and or logic. But we have a lot of the same problems as 3-state buses. That is to say, we have to sequentialize our otherwise parallel system. With Wishbone, you can also do data flow. In this particular case, Wishbone allows you to, well, in fact, you have to, because there's no 3-state interconnects. Wishbone has a separation of data out versus data input on their buses. So connecting Wishbone buses is a lot like connecting RS-232 devices, where you tie the transmit pin on one device to the receive pin on another, vice versa. In this particular case, we exploit that by taking multiple devices, which may or may not be masters, in the more traditional sense, and we've just put them in a row, back to back. Now, it could be just a flat strip of devices, or we could wrap the ends around. Thus forming a dual counter-rotating ring. There are a different set of options for this, all of which are generally considered data flow. Now, if you were to read the B3 specifications, this would be considered a pipeline, but because now B4 has a separate pipeline mode, they've renamed this to data flow. So you may see slightly different descriptions of this. Fun fact, if you have an x86-based computer, and that x86-based computer is running hyper-transport technology, this is almost exactly the way hyper-transport actually works under the hood. Just thought I would throw that out. The most common interconnect that you will find with Wishbone, simply because it's easy, it's actually fairly trivial to get working, is called a crossbar switch. In this particular case, every slave device that you have on the computer has its own arbiter. And that arbiter is wired to its own set of masters. Now, in this particular case, I've got 3 masters, 4 slaves. All 3 masters are wired to all 4 slaves. This is a fully interconnected mesh network, essentially. Doesn't have to be this way. You can optimize this for area and power as necessary, such that only the first 2 masters address the first 3 slaves, for example. Brilliant example of why you would want to do that. It's probably not a wise idea if your microprocessor is able to fetch instructions from I/O space. Bad idea in general, unless you have specific requirements. But this is typically a very expensive interconnect because, as you can see, there are a lot of buses, and buses take up lots of lookup tables. You're going to eventually run out of dedicated interconnects between logic blocks, and your synthesis tools will then start to use lookup tables as wires. Unique to Wishbone B4 pipeline mode, but not documented, and so far as I'm aware, I'm the only person who really who actually put any thought into this, is you can actually do a different kind of crossbar switch that is actually packet oriented. So packet-driven buses like HyperTransport or Rapid I/O, which I've talked about before, these are systems that take your bus transactions, wrap them up into tiny little packets, and they ship them out over a serialized line, right? But when you think about it, when you separate the address generation phase and the data response phase, if you have the ability to do that, you have the ability to wrap an address generation chunk of data into a message, and you just send it out over a serial bus. Likewise, if you can just asynchronously receive data back, then you can just receive that over a separate channel as well. It doesn't matter that you get it all in parallel versus bit serial or anywhere in between. So it makes sense that Wishbone B4 does have some capacity for handling packet-oriented interconnects as well. Although no one, to my knowledge, has done it. It is something that I'd like to explore in the future, but yeah. So, applications of Wishbone in Kestrels. So I've already shown you the Kestrel I, which was a 65816 based computer that I made that used 3-state shared bus. The Kestrel II is my first design that sits on an FPGA. It actually is built for the Nexus, the actual Digilent Nexus 2. And it uses my S16X4 family CPU. It has 3 block RAMs, each of which are 16 kilobytes in size, one of which is dual ported to the video core, the MGIA. But otherwise, everything else is just basically an emulation of a shared bus. My initial attempts at getting a 64-bit processor working for the Castrol III involved just replacing the CPU. So we have the KCP 53000 that has separate instruction and data fetch ports. We run that through an arbiter so that we combine them to a single bus. We adapt it to Wishbone B3, and then I have another bridge after that, which narrows it from 16-bit down to, 64-bit down to 16-bit. So as you can imagine, there's a lot of intervening logic from the CPU all the way to the final bus. I would like to eliminate that, especially when once I got enough circuitry to actually run this with external RAM. I noticed that I had a big problem with timing, basically getting everything fast enough that it would actually meet my performance criteria. So now what I'm currently doing is I'm targeting a completely different FPGA, and for various reasons that I won't get into here. But that fabric is much smaller than the Spartan 3 device that I have on the Nexus 2. So I have to cut back on a lot of stuff. So what I'm doing now is I'm designing a new version of the CPU that directly interfaces to a 16-bit bus. I'm no longer working under the assumption that I have 64 bits and that I can just narrow it down to 16. That saves a lot on cores. On lookup tables. So really all I need is to preserve is just the arbiter so that I can control which of those ports have access to the Wishbone bus. The Wishbone bus is now B4 instead of B3. And basically I've got 2 new cores involved. I've got the IPA, the initial program adapter, that is my ROM emulator in a sense. Basically, it feeds off of RS-232 data streams, and it works exactly like example processor. It works very much like the F18 core does in the Green Arrays chip, where when the system boots up, basically you want it to fetch from ROM, but the ROM is actually this IPA thing where it actually blocks the processor. So it'll actually halt the CPU until I actually spoon feed it a chunk of data. The SIA is the full purpose UART, basically. That's the serial interface adapter. IPA basically piggybacks on top of the SIA. And then I've got a RAM bridge that talks to external static RAM, and that is it. So in a sense, I'm going back to the Kestrel I design, but albeit with a 64-bit CPU driving a 16-bit bus. It is intended to be a properly pipelined interconnect. I'm sorry, processor, I should say. It's a properly pipelined processor. And one of the phases of the pipeline is, of course, the load store unit, or the memory chunk. It has three broad categories of ports. The inputs from the top are from the arithmetic logic unit, and the stuff going down to the bottom goes back to the register file. The stuff on the right, though, that's the actual Wishbone bus. And if we were to zoom in on that, we would see a circuit like this. Basically, it's a block diagram of the actual Wishbone circuitry itself. The A register, as you can imagine, is the address register. And the DO register is the data that we want to send out. Now, in this case, it could be 8, 16, 32, or 64 bits wide. Your particular application may have additional widths if necessary, or even fewer. It doesn't really matter. But the thing that makes this work is, notice that I've got two blocks down there called CDFFs and RDFFs. These are the command D flip-flops and the receive or response D flip-flops. And you'll notice that they're both initialized at the same time with the same values, but they otherwise operate completely independently of each other. There's no connection, there's no loop, if you will, between the command side and the response side. And this is something that will greatly help with synthesis as well, because with the Wishbone B3, whenever I would run it through my synthesis tools, which is Yosis, as well as well, I can't remember the name now, but Verilator. Like whenever I run it through Verilator, it would constantly complain to me about, oh, you've got this loop that would cause your synthesis to, or your simulation to deadlock. And that's very annoying. So the fact that there's no connection anymore between input and output is a huge burden, huge relief of burden, design burden on me. So when you try to build something like this, it's probably best, actually, in my experience, to start with the receive side first rather than the address generation. So basically, you just kind of assume that an address has been sent already. And so what you do is you have this shift register, which in my particular case, I load with D-word, word, and H-word signals that basically say, okay, I'm receiving a 64-bit, 32-bit, or 16-bit chunk of data. And then basically we shift this register. So at any given time, only one bit is set. So it's like a ring counter in a sense. But we shift this every time we get an acknowledge input. And when that happens, as long as any one of those bits is set, you'll notice that I have a circuit there that generates the cycle output for Wishbone. So as soon as you need to request memory and you load this register, boom, that asserts the cycle output that requests the bus, basically. But that signal does not negate until all the registered values we need have been brought in. They also are used to select which specific input port, or I'm sorry, which input register is used to capture the data off the bus. So in a sense, this small circuit actually replaces the Furcula to Wishbone converter, the 64-bit to 16-bit bridge, and it actually meshes extremely well with the rest of the pipeline architecture. So this is actually saving quite a number of lookup tables for me. The command side is actually almost identical, and it also has a shift register. You load it with the same inputs so that they remain in sync, but this one is shifted based on a stall input. Now, I didn't discuss a stall input or not, but basically Wishbone, when you're sending stuff out over the bus, you have a way of throttling that as well. That's what the stall I input is. But as long as that input stays low, Wishbone says you need to blast your commands all the way out as quickly as you can. So that's what we do here. And then again, based on the output of the shift registers, we select which portion of our data that we want to send, as well as the specific address that we want to appear on the bus. And that's really it. So again, error and retry, these are optional signals. Acknowledge is a compulsory signal. Something has to terminate a bus transaction, otherwise the bus will deadlock. These also will terminate, but these are optional signals. So for example, if you're building a microprocessor without an internal MMU, you might be inclined to expose an error input that basically says whenever this thing is asserted, you might want to cause a trap. But in order to terminate that bus signal, you have to zero all of your D flip-flops, all of them, both command and response. Now, if you look, some older processors like the 68020, 68030, Intel 80386, for example, they have retry inputs. Now, these are interesting because when a processor commences a bus transaction and you assert retry, the whole point of this is basically like Ethernet CDMA in a sense. Basically, it tells the processor, hey, back off, wait a while, and then try again, right? So what you do to do that is you reset all your DFFs to their initial state. And then I didn't document it here because I ran out of room, but basically in addition to this, you also have an additional wait state generator that kicks off as well. But because your initial your DFFs are set to an initial state, as far as your Wishbone circuitry is concerned, it is exactly as if the CPU has just restarted the bus transaction. And all of this comes for free, basically, just by using that particular architecture, using that shift register arrangement that I described earlier. And therefore, for me at least, Wishbone B4 pipeline mode is a lot easier than getting things working with Wishbone B3. And that's pretty much it. It is Wishbone architecture is very simple, incredibly simple to implement. I can't speak highly enough about it. It's extremely performant, and it lets you do some pretty amazing things. Any questions? Yes.
Why Wishbone, not some of the other alternatives?
Why Wishbone and not other alternatives? So let's see here. AHB is essentially proprietary technology. AXI it's an open standard, certainly more open than AHB is, but it is slower than Wishbone, and it takes up a hell of a lot more resources. OCP has really weird licensing requirements. So basically Wishbone is a happy medium of... oh yeah, go ahead, please. It's a very happy medium between friendly licensing terms, adequate performance, and very easy to implement. What's that? I would imagine it's the same because they're both ARM products. And if APB is fair game, then they probably changed their licensing to compete. Extremely well documented. Yeah, AHB, APB, and AXI. If you want to look at their specs, ARM actually has them up on their website, and they go through a lot of excruciating detail. Actually, compared to Wishbone specifications, they're almost over documented. They're very, very well documented indeed. Yes.
What was the deal with that? There are tri-states that piece up 5LP and for the routing fabric. I was wondering why.
So the question is why avoid what gotchas to look out for when using 3-state on your fabric. So you have capacitance issues. So if you're routing from one end of the chip to the other, you end up with these long spindly wires, basically. There's no way to control them, and there's no, unless you do manual place and route, there's no way to control the lengths of these things. You're at the whim of your routing tool, and so each line on that bus is going to have a different capacitance, a different inductance, which means a different impedance as well. So when you drive this thing with a reasonably slow signal, it may work great, but as soon as you get up to 30 megahertz, 50 megahertz, thereabouts, once you start getting into RF frequencies, then you're going to find that signals, your skew is going to be different. So signals might arrive before or after the preferred time. That's one possible problem. The other problem is you may find through a bug in your circuitry that you have multiple devices driving the bus at the same time. That causes contention. And so you end up short-circuiting inside the chip, and that will actually damage the chip itself. Cool. Old FPGAs, yeah. Yeah. So I gotta go. My time slot is up here. But if anyone has any additional questions, I'm here all day, right? So cool. Thank you.
All right, how's this? Is my audio good?
Sure.
Yep. All right, so I'm going to be talking about work I've been doing with the green erase chip, particularly making alternative tools to enable me to work with it better. So these slides are a little rough. I'm also full-time employed, so I guess that was made for me. That excuse is already made for me. I'll reuse it. I actually like those last slides. They were pretty good. I'm mostly talking about alternative green erase tool chains that I've been working on. Compiler, loader, simulator, stuff like that. I'm going to demo it. Compare it to other tools. There's other ones out there. Green Erase made some. Some other people made some. And then kind of a smartwatch presentation. I'm saving that till the end because it's super cool, so you have to stick around. Other pending projects that I may work on. So I don't think most people here probably already understand why I would want to work on this. The green erase tools are pretty hard to deal with from a person that's kind of used to modern conventional tools and operating systems. It kind of goes like you find this amazing chip, and then you have to work with it through these tools. And this chip it's part of what makes it so interesting and so unique is, it does everything its own way. It's pretty obscure. It has its own way of doing everything. Not only like each computer, but you have all these computers, and to be able to program all these computers, you need to kind of rethink the approaches you take to programming, and that makes it a pretty hard thing to approach at first. And then on top of that, you throw on the grain arrays tools, and it's just like all these layers of obscurity, and I think it's pretty hard for people to get into it, kind of to see through all that and kind of realize the potential of this. For me, this started out because I just needed some way that was much easier to interact with Linux. I didn't want to have to do things manually every time I make a change, and kind of, because I was working with chlorophyll, so we were generating programs outside of Green Array's IDE and needed to bring that inside. And that was annoying. And I want to be able to easily modify and extend it, and I didn't understand Forth at the time. I still barely understand it. I've just started to learn it more this month. Actually, I've been reading starting Forth. So, but at the time, this is like, it's too much. And so there's the motivation. Other people, it seems, have had similar ideas. I looked on GitHub a little while ago, and seems to be the start of quite a few approaches, most of which seem to have fizzled out, except for the ones I've starred. Mine, of course, because I think it's the best. James Bowman has worked on some as well. It's kind of a lower level, or kind of like an assembly approach. I'll talk about it a little bit more later. But I started because it seems relatively complete, it's usable, and people are writing cool things with it. Yeah, that's annoying. But so this is about, this is my GitHub repo, this is where it's at. And the goal is to really provide a complete alternative to Green Array's tools. More flexibility, use it within a Linux environment. Other things, it looks like I was getting into, but I didn't. I mean, you get the idea. It tries to be compatible with the Green Array's style Forth, array Forth. I want to be able to, I don't want to like rewrite absolutely everything they did, just like the compiler and stuff. So, for example, I have the SRAM code that I copy out of their IDE. I have a script now to convert from whatever their color Forth thing is to the format that I use. Actually, I didn't write it, somebody else did it, but I adapted it so it's, it gets rid of things like the gray words that don't make sense here. And compiler, assembler, boot streamer, simulator. It tries to be like complete, but it's not really complete. It's kind of complete in the ways I've needed it to be to work on things. So there's lots of things that Green Array's tools can do that I can't right now. Like for example, with the boot stream, I can load boot streams in through the async port node 708, and I can load them in through, I think it's node 300 on the left. So you can load boot streams through the host chip into the target chip. I have a graphical interface that I've built in Emacs that the simulator is based on. It also has an Emacs mode, of course. There's the bash commands so you can run all this stuff from your shell so that you don't have to use Emacs. Because, yeah, yeah, it's hard to sell a weird chip and be like, but you get to use it on Emacs, but I like Emacs, and it's a production environment, and it's all written in eLisp now, or most of it, because it was previously written in Racket, and this is why I originally had these tools, because it's, see, chlorophyll was written in Racket, so I just started to write this in Racket too, but then I wanted to make the Emacs mode, and I wanted to make the simulator, I tried to use the Racket language, or the Racket GUI language, and it was a disaster. It's much easier in Emacs. And I thought it would be easy to bring all the code, because Racket's very similar to eLisp, bring it all into Emacs, have everything there, don't have to worry about communicating stuff back and forth, like requesting information from the compiler and all this stuff. So it's pretty much all in eLisp now, except for a program to load it onto the chip, because I had problems in eLisp with asynchronous stuff, the terminal stuff. Yeah, this is only tested in Linux, It's all Python or Lisp, so it's probably, I don't see why it wouldn't run other places. I think I've hard-coded some file names like /dev or something that maybe don't exist on Windows. Yeah, so it's usable. It's easier for me because I knew it and I know where the bugs are, so maybe it's rough for other people, I don't know. So from the command line, you can use GA. Just GA with a file name just will dump just a JSON dump of, it contains the file name, the compiled data, boot descriptors, the assembled data, and the boot stream. -P, you can print out pretty. It's just formats it so it's easier to read. You have, contains the word names in there. The, you can see it, columns for compiled, assembled, and disassembled, which should be pretty similar to the compiled, hopefully, if there isn't a bug. So it's, it has been useful to find it. It's -C is supposed to print out your node usage. I tried this out, and it turns out there's a bug in it. It's totally fails. All these commands are with this code that's on the top left. And I probably broke it a while ago, but haven't noticed it. This is probably kind of the rough aspect of these tools, mostly because I have the interface now, and so I don't really use it anymore. And to load it, you do gload and the test and then the device file. Oh yeah, there's other commands. You know, you can just dump the symbols or whatever, whatever you want. I'm gonna skip this. Hold on, where am I? This is empty slide because let's not worry about that. The Emacs mode is. It's not like it's a little different than normal. Like most Emacs modes just highlight the words, like it pattern matches and has some regexes and stuff. And I had a hard time with it because I guess it can take array forth. Like you can just use any combination of characters, and was having a rough time. So it takes it parses everything, takes information, or the parser will kind of spit all these tokens that have the buffer positions in them. And so that's fed to both the mode and to the compiler. And so the mode knows where to go and highlight stuff. And this works well with Bowman's interpretation of array forth as well. Apart from the comments, the words are all the same, so it usually works. So this is the graphical interface. If you're in the Emacs mode, or in the array forth mode, hit Control V. It brings up this view. The nodes are colored for their usage. The green node is like the cursor position, so you can move around on it and select them. So, and then it displays the compiled code. Yeah, I use this mostly if I care about how things are getting laid out in the memory and it's not obvious. Then you can kind of watch how it gets updated live. And this was originally intended to be kind of a I had this idea of having this is sort of like you approach your whole project graphically. So this is like your whole view of your whole project, and you manage everything through, and you put all your settings into it and everything, and it saved all the data into kind of like a file that it would load up from. And I got into all sorts of problems with that. I was fixing too many bugs with it, and then I didn't really have a use for it. I wasn't really solving a problem, and I just kind of stopped because it was wasting my time, I think. So I didn't really know what I wanted out of it, I suppose. So now it's mostly just a view. It's not stateful or anything. And yeah. Oh yeah, I was going to demo this. So So this is our program. We're going to add two numbers. Control V brings up the demo. I'm having the display is much lower resolution, so yeah, this is an Emacs now. No, so I want to go down. You know, the hardest thing from all of this, how do I make this bigger? I think one of the hardest things I had was when I leave the buffer to make the selected node gray. it was hard. So you can navigate around on here. You navigate around the chip in sort of the same way you do navigating around in an Emacs buffer, except instead of characters, you're navigating around the nodes, which is useful if you know the commands already. Right now, there's no other way to select it. You can use the arrow keys too. So once you're on the node, you can hit enter. You can go to the source. You can view on the right the compiled code. So from the source, and I say add something, or save, it immediately gets compiled and updated. Make a new node. 305. All right. I don't know what you would want to do here, right? I don't think there's much else in this node right now. It's mostly, yeah, usable for looking at nodes and kind of visualizing the whole application. So in the way that you, like for example, this one is the code that reads from an accelerometer. And so it gets much easier view of what's going on. You can see node 708 is all the code for asynchronous communication. 705, I think, is Crystal. There's a path that goes to the left to node 600 to, oh no, node 708 is talking to the accelerometer, so it's bit banging I2C, and then node 600 is sending the words out to the computer. Yeah. Yeah, the simulator. So it's, you know, it's kind of like the green array simulator. Or I guess suppose any simulator. You step through the program and you view the internal state, and you can set breakpoints. What else would you want to do? I think it's easy if I just show. I've set it up. So this is based, the simulator is based on the same view as the, what I just showed you, but it's slightly different. Instead of showing you just that compiled data, it's decompiling the RAM. And so some things are not as easy to see. For example, when you compile, it doesn't understand that like the value in a word is supposed to be a number or interpreted as a sequence of instructions. So it decompiles everything as instructions. So when you're instead of hitting Control V to bring up that view, you can hit Control S, and that brings up the simulator. So I've done that for a simpler program. This program is from AB004. It's the array forth note on, or the green arrays note on port execution. So in this example, node 600, node 609 is just used as memory for node 608, which can address it. So let's see, a few things. First off, directly to the right of the chip view is this column. You can just ignore that. I'm still kind of experimenting with how I want this, what I want on the view, or just getting things up there. So right now, like whenever I make something new, I just throw it on here, and it's kind of disorganized. And in this case, I needed to. It's kind of the same problem we have with this sort of thing, where you have a node that's writing to its memory, to its RAM. And right now, on the right is the RAM, and it follows the position of the instruction pointer. And so as you're following around, which is usually the most useful for me. And the problem is that if it's then also writing to like to some lower, anywhere else that's outside the window, you can't see what it's writing. And so the idea was to have kind of two views of it, so you could kind of have a dual view. But I haven't finished it yet, so I didn't want to delete it and risk breaking something right before the demo. So a few things. We have on the bottom are the stacks. On the left is the data stack. On the right, the return stack. Then there's some registers, A, B, P, I/O. I is the instruction register, and next to it is a decompiled word. On the RAM view is, you see there's the blue and then the sort of pinkish words underneath it, A and B. A is the blue one is the currently executing one, which is the same as I, and P is the location of the instruction pointer. So let's see if I'm going to show you with the simple one. Just adding two numbers. So Control V. All right. So it's pretty clear here what's going on. There's only 3 words in this program. We're loading 1, we're loading 2, and then we're going to add them. So we're executing at word 0. So P is incremented to 1. The current instruction is highlighted in yellow, which means that it's about to be executed. It hasn't been executed yet. So when you hit S, that gets executed. Moves to the next one. So you see on the data stack, it's loaded 1. Do that again. Now we load 2. Hit plus, and on the data stack you get 3. So it's pretty. I think that's pretty straightforward. So this example kind of shows how you can work through, how you can visualize a program executing. It uses a port execution feature, which I think is one of the pretty cool things about this chip. So node 609, all it does is to execute on its right port. So when we step through that, the first step, it's going to jump it to that register. And then by I, you can see it's by port, and it's a fetching state. So it's suspended now. It will echo on the bottom left if you continue trying to step it. Right now, S just steps a single node. So back in 608, let's see, you can see it starts out on the far right. It prints the name of the word location, and automatically starts at the word main. So main is, first it's putting right into its register A. So it reads that value, puts into A. And the values, the names of known port values are printed by the value, by the registers. So you can see R -- and IO, because I don't have all that stuff memorized. And then we load 5, load 1, call the routine store. The address you can see pushed on the return stack. I'm going to step through that. So now it's suspended because it's written to its right port. It should have written two things to its right port. On the right side, it's received one of the words now, so it's no longer in fetching mode. It's received this word at P, so now it can read that value, read it, put it into A. And now it's fetching again. Now back in 608, return, jump to 4, read the value that we're going to send it, or send that word and then send the value that we're sending, which is 5. Return, go back to 609, reads the value that you sent it through at P, which is 5, sends that, puts that through A. So now if you go to 0, you can see the word 5. We've overwritten the instruction that used to be there. So right now, if you hit, yeah, so stepping through the rest of main, we have a loop, 10 for, basically you have an index value. We're going to double that, and we're going to store that at that index. So index I has the value 2i, and we're going to send that to the other node. So you can step them all. Capital S steps all the nodes at the same time, which maybe should be what S does. I'm not sure. But at the bottom, it prints how many nodes are currently active. Right now we have 40. Step again, 22, 12, 8, 6, 5. Yeah, so nothing's gotten... Crap, I have Slack open on some other tab. Yeah, so right now I'm just hitting S a bunch of times. I don't have a way of just running it, but you can see it's starting to write the values into this node. So we're looking at the lower memory of 609. While 608 is running and writing the values into it. So there's a lot of little things like that that I don't have yet, and I kind of add them as I need them. Let's see, what else can we do here? In the simulator mode, I have a lot of browsers open, so Jesus, why are people working on the weekend? So now you hit G, you can reset it. Unlike the other mode, when you save the source in when you save the source when you save the source file that's being simulated, it doesn't update the simulation. But if you save that and you hit G, you can reset it, or hit G anytime. It just resets everything. You can see we have the RAM fully loaded in here. So in most of these nodes, okay, this is, see, I can pkill. Okay. So we have everything loaded. So the current state of all the nodes is to jump to warm. You can, except for the ones that we've loaded, are the only ones that are not pointed into some position in RAM. What else? Oh, you can browse through it and stuff like that. There's all sorts of little helpful things. Or yeah, I think that's it. Yeah. Any questions about the simulator while it's got it open? Yeah, so we did that. So comparison, how does this compare to the green arrays tools? Well, the compiler itself, I think I have everything they have and like 10 times what they have and 100 times the source, and I don't know, I've got everything but the elegance. It's the loader is, it's what I need. I think it's a lot larger than it needs to be. It visits every node, even if I only want to load code into one. There's only limited options. I can't load a boot stream from Flash right now or something like that. I haven't looked at doing that. So the comparison to their simulator, I think I can do everything they can do, but I can't. It's the interface obviously isn't as nice, or at least it doesn't tell you as much. The part that's I miss the most I found is the view from each node on which nodes are writing to you or reading from you. That's useful, and I'm gonna add that at some point. It's also really slow. I don't know how fast theirs is, but when I tried this, it was embarrassing. I don't want to share that number. I don't really remember anymore, but I mean, it's running an eList, so it's going to be slow, but I didn't think it'd be that slow. Yeah, booting Flash, that's not supported. The memory, I haven't tried Flash. I assume it's not too hard. SRAM works. The interactive development is probably, I never really got to use it with their tools, but it looked like something that would be useful. It looked pretty powerful. I don't have that at all right now. I can't reach into the chip and execute some word on it and kind of read its memory or look at its stacks or whatever. Maybe I will at some point. So this is how it compares to what I think is, or what I've seen as the only other viable option. I haven't really looked into everyone else's GitHub stuff, but this is sort of the style where you have one word per line, and it's like assembly, and it's really the differences are kind of trivial. There's this is the program on the right side that sends data out at 708 over the async port. And the same program copied, just changing the style. So I guess it's Firefox somewhere. Changing the style so it uses my tools. And I just find it a lot easier. On the left, you have a loop that calls 2 words, and it's the equivalent on the top if you do it 1 word per line. I just visually, I find it a lot easier. And I tried last night to write a little bit of this. And wait, how much time do I have?
13 minutes, 12 minutes.
Okay, we need to transition quick then. And yeah, I found all sorts of bugs from that because I wasn't used to it mostly. Okay, I'm going to skip a few things and go to this smartwatch presentation because it's really cool. And I can come back if we have time. Wait. Looks like I accidentally deleted one of the slides. Well, it was the title. Oh, Jesus. Why is this stuff so hard to deal with? View. Present. Right. So, this is a project that Mark Flamer's been working on. He calls it a wearables platform. It's like a smartwatch based on the green arrays. He was working on this, I think he maybe like sometime last year or more. It's been a while since he did work on it, but I contacted him a little while ago, a few days actually, because I was interested in this again and wanted to help work on it. And like, I don't know, a day or two later, the thing just showed up at my doorstep. That was incredible. So I've got it here. I'm going to pass it around. This is really all work that Mark has done. If I didn't, I wouldn't put my name on the slides. He even did the slides. That's why they're nice. So I'm going to pass this around. I couldn't find tape for some reason in my house to tape this together, so the battery is kind of loose. Just be careful when you're holding it. I mean, it's just connected with a wire on the pins. It's really not that bad.
If you're interested in seeing it, just come up to the front of the room.
All right. Okay. Sure. Sure. Yeah, I'll leave it here.
It's a good idea. It doesn't mean we shouldn't do it.
Yeah. I don't know. It seems safe to me, but yeah. So why would you want to do this? Maybe we should skip this slide. I think this is obvious. Right. It's an incredible computer. It sleeps all the time. Like when you don't need it to do something, it does nothing. And when you need it to do something, it's just like instantaneously throws 144 computers at you. It's great. So who wouldn't want to put that on your wrist? You know. I think that'd be so cool. So a lot of potential things we could do with this right now. You know, it's pretty basic. So this is the computer or the watch. This is me this morning trying to model it, trying to be a watch model while I work on a green arrays board and try and balance out my wrist. So that's all I could do. It was much harder than it looked. So the hardware, obviously green erase chip. It has this really neat e-ink display. I'm not really sure what kind of e-ink. It's not like the normal like Kindle e-ink, but it's very low power. Flash. Mirasol. How do you know that?
It's a reflective. That's one of the ones that's made the very low power color at that small size.
Cool. Yeah, it's pretty neat. I unplugged it once because there's no reset button. I tried to unplug it and to reset it, which I normally do, but the color didn't go away. It was weird. It's like it sticks around for a while. It was like,
It's a static display.
Okay, yeah, that's why.
Power won't change
Yeah, it goes away like after like 30 seconds. You can start to see it like fade. It's not like the true e-ink where you can like leave it on there. Like the e-ink thing, I think it uses like some static thing to move some ink particles up or whatever. But I think it consumes, I don't know, some microwatts or something. I don't remember exactly. I can't really.
It's charge-based, changing MEMS mirror. Okay, so they're consuming power. No, it's a static, but it changes, but it loses it.
Well, yeah. And it's got some other things. Accelerometer, gyro, microphone, analog joystick, buttons. All right, so here's the outlay of the software as it is today. We have, like, working is the 2D graphics pipeline. Node 205 right now is like, it has a demo program in it that is printing out if you come look at it. Well, you saw it on the screen, it's the same thing. Some characters and rectangles, some circles and rectangles. Right now, the rectangles and circles are implemented. Hopefully, characters and lines are coming soon. We have a crystal timer. Lots of this stuff right now is sort of missing drivers. I think the joystick, the buttons, microphone, stuff like that needs to be implemented. SerDes is wrapped around. The clock is distributed around the chip for a timer. I think the display needs I think Mark said it was it needs to be updated every second or a 1 hertz timer or something like that. Yeah. You guys want to help? Looking for more contributors. You should get in contact with Mark. Might send you a unit. I think I have the only one that is actually assembled right now, so he has to make you one. What else? I probably missed a lot of things. Mark is probably listening to this and be like, why didn't he say that? Why didn't he mention that? I don't know. Yeah. Questions about this watch? Yeah?
Can you write the board
Oh, I forgot. There's, see the big purple square? Well, it's a green erase chip you write for it, right? This little.
Yeah, but can you, there's like a Casio watch there. What are those little Casio watches where you can write for?
Well, right now there's no virtual machine.
Oh, that's right. It's not interactive at the moment. But,
Yeah.
yeah.
I mean, you can write, like, if you consider the assembly or whatever, the instruction set for this chip fourth. Do you consider it fourth?
Do I consider it fourth?
Yeah.
It's a stack-based instruction set, so I guess.
Yeah. But you, yeah, right, yeah.
Mike, is Mark using green array tools or yours?
No, Mark is using James Bowman's tools. Yeah.
The difference going from Chuck's to James to you have to trust more people's work.
Yeah.
I'm working with Chuck's stuff. I'm basically trusting one or maybe two other people that I know personally. And then you come up with this kind of interactive. Chuck and Greg are at this point the main. Actually, Greg at this point is the main stuff. Charlie is keeping a whole bunch. And yeah.
Yeah.
You've got the whole Linux and all the rest of the stuff in there that you're trusting along. You have a basis for trusting that, and Chuck never did. So.
Well, I don't think, from my perspective, the way that I use it, the Linux isn't a problem because if I use green erase tools, I'm using Linux anyways, right? Because I have to run this green erase tools inside Wine, which is like this massive program in itself, on top of Linux, so I have kind of all the pain of this minimalistic system and none of the real benefits of it. But, because you can put this on, I guess you can throw away all this Linux garbage stuff and just put their tools on the hardware, right?
Yeah. You can run polyforth on the 144.
Yeah. I've really only recently started to appreciate that you can actually put this on the hardware and you can get rid of everything and just have this as an operating system and an editor itself. I didn't really grasp that for a while. It's pretty neat, but I mean.
Yes.
Yeah.
You're using the development system as a development environment. So you're using like green array tools. It's tools on green. Yeah. It's all a big kludge. Is that the right word?
What?
It's a amalgam of stuff. It's a big stack.
What? Oh, for the whole Linux thing?
For you to do development with Mark.
Oh, yeah.
It's a big stack.
Yeah. Because do I understand it right that those tools were designed to like boot off floppy or something on the hardware? Like
initially, all the tools fit on a single floppy. Yes. Including the hardware simulation and the chip design. Everything is on a single floppy.
Yeah. I don't want to go back to floppies, but
We would not either. Green arrays would not do that either.
Yeah.
So, in fact, we're not going to go down. Green arrays is moving into polyforth, running either on a chip for immediate development or on a PC for whether it's under Linux. It's the standalone forth on PC to do the speed, the simulation and stuff, and the management of files and the interface with the rest of the world.
What about putting everything on the fourth virtual machine running on this chip?
It doesn't. You can't simulate the chip fast enough running on the chip. It's just. It isn't. That's not where its speed is. That's where having the PC Apple is really, really useful.
But it is possible besides the speed concern. Besides the speed concern, it's size, it's possible. You're saying.
Excuse me?
You're saying it would be possible if not for the speed concern of the simulator.
If we could interface right now, the flash and the memory interface can't interface enough memory to make
Yeah.
I think where you were entertaining the idea of like having a second microcontroller to control for the GA144, like an ESP.
Or maybe the other way around. I don't know. Yeah, I was thinking about the idea of having a green arrays chip with an ESP chip. So ESP would mostly be there for the Wi-Fi. You could do, I mean, you have a large programming space, you can do that too. And you could also use it as memory to load boot streams for the green arrays chip from. But that's not really a substitute for an x86 desktop or anything, Yeah. Time? But I have more slides.
Have a look at his watch up in front of the room. If you're interested in joining me for dinner.
Also, if you do go on the GitHub repo, keep in mind that I haven't updated the README in over a year. So it's a lot of data. I'm going to fix that soon, but, Yeah. It doesn't have a backlight right now. So you have to kind of tilt it around to start your two sides of it.
I'll say goodbye to everybody. Nice.
We missed the T slides.
Next time.
I didn't think I'd run out of time, honestly. It seemed like so much time.
Well, it always does. Well, folks, that was a great talk. We'll see you next month. We're done for now.